All right, let's talk about algorithm analysis. So, algorithm analysis has to do with systematically examining algorithms to characterize when they perform best. So, usually we ask two questions. How much processing time does an algorithm take to complete? And how much memory does an algorithm require? And usually there's a trade-off between these two. If you have a small amount of memory, you may choose a memory-efficient algorithm. If you have a slow processor, you may choose a processing-efficient algorithm. But very rarely can you optimize for both of these things. And that's where the trade-off comes. You usually have to pick one or the other. So in the early days of computer science, we measured algorithms. We measured the amount of time it took to complete a program. So we might say this quicksort algorithm could sort 1,000 random integers in 0.142 seconds or something like that. Okay, so quicksort, 1,000 random ints. And that took 0.142 seconds. Something like that. And then we would, of course, compare it with maybe another algorithm, maybe bubble sort, which also sorted 1,000 random integers. Okay, but it took this particular algorithm maybe 0.256 seconds. And then what we would say, we'd always say, well, this was tested on some particular machine. So maybe an IBM 701 with 16 megabytes of RAM. Okay. That's how we used to kind of measure how well algorithms performed. We just run the program and figure out how long it took to complete. There's some problems with this approach, though. So there's some questions we might ask. Can these results be duplicated on another machine? Or in other words, is there something about the 701 that made quicksort algorithm run faster? Maybe it has more cache memory or an extremely efficient call stack or something like that. Another thing we could ask as well, was bubble sort written with the same care as quicksort? So maybe the same effort wasn't taken to make bubble sort as good as it could have been. And then lastly, probably the most important thing is, are the results same with 1,000,000 integers? So we saw there's a clear winner with 1,000 integers. If there are 1,000,000 integers, does that change the result? So what we needed was a way to compare algorithms independent of hardware, programming language, and the skill of the programmer. Okay, so generally the larger the problem, the longer it takes to solve that problem. Sorting 10,000 integers should take longer than sorting 1,000 integers. And algorithm efficiency is usually stated as a function of the problem size. So we usually talk about n. N typically represents the problem size, or the number of things to process in an algorithm. So if we're sorting 1,000 unsorted integers, n is 1,000. If we're sorting 10,000 unsorted integers, well then n is 10,000. When analyzing an algorithm, we always need to count something. So we usually look for a fundamental operation in this algorithm that is representative of what the algorithm does. And we call this the critical operation. This critical operation is usually performed on all n items in the problem set. So in sorting algorithms, we usually use the comparison of values as the critical operation, since comparing two values is fundamental in almost all sorting algorithms. Okay, so maybe we remember our good old sorting algorithm called bubble sort. Let me remind you if you don't recall. So let's say we had this array with these values in here, and our goal is to sort them. Okay, the way bubble sort works is we always look at adjacent pairs of values. So we go through every single adjacent pair, and we basically say is the left value greater than the one on the right, and if it is, we swap them. Okay, so in this case, is 12 greater than 7? Yes, so we would swap these. Then we'd say, then we move on to the next adjacent pair. Right, so we'd have 7 here now and a 12 here. Is 12 greater than 13? No, so we'd go to the next adjacent pair. Is 13 greater than 6? Yes, so we would swap those. 6 would go here and a 13 would go here. Okay, so after we do that once, our array is going to look like this. We're going to have 7, 12, 6, and 13. And one thing you'll notice is every time we do that, go through all these adjacent pairs, one more item is in its final sorted position. So I'm going to draw this imaginary line here. Everything to the right of this line are sorted elements, and everything to the left, these are still unsorted. Okay, so we could do this again. Look at these adjacent pairs. So we have 7, 12, 6, and 13. And again, we'll do our left and right comparison. Okay, so 7 greater than 12? No. Is 12 greater than 6? Yes, so we'd swap these. Is 12 greater than 13? No. Okay, so what we're left with now is the array that looks like this, where we have 7, 6, 12, and 13. And going through that process, again, it put one more item in its final sorted position. Okay, so this part of the list is sorted, and this part is unsorted. Okay, so I won't continue on here, but that's the basic idea of looking at adjacent pairs. So the code for bubble sort might look something like this. Okay, so I'm going to start with the code that looks through all the adjacent pairs. Okay, and we're about to come to our critical operation here. This is the thing we want to count. And we'll use the count of these critical operations to compare sorting algorithms, because pretty much all sorting algorithms will look at two values to see if one is greater than the other. Okay, so we'd say something like if vec at position j is greater than vec at position j plus 1. Okay, if that's true, we're going to swap j and j plus 1. Okay, so notice here I went to not the size, but the size minus 1. That's because here I say j plus 1, and that this stopping at vec.size minus 1 just makes sure that when j gets here, j plus 1 is right here, and we don't go beyond the bounds of the vector. Okay, so this will go through every single adjacent pair, and it will push the largest unsorted item to its final sorted position. Okay, but this puts one number in that final sorted position. In order for us to get this totally sorted, well, we need to do this, about n times. Okay, and I say about n times, or vec.size. Actually, if we stop one short, what would happen in that case is we'd have basically a sorted part over here and an unsorted part that's exactly one element. But we know for sure a list with one item in it is by default sorted. So we can stop one short here too, and we will, this is our typical bubble sort algorithm. Okay, so let's try and analyze this. We have our code here. Okay, so what did we do? Well, we went through n-1 comparisons to put one number in its final sorted position. That's the inner loop. And we had to do this n-1 times. Right? So one time through the inner loop, we'll put one item in the sorted position. If we do that n-1 times, the entire thing will be sorted. Okay, so how many times is this? Well, this is n squared minus 2n plus 1. Okay, so when n is equal to 5, we could just plug 5 in here. That'd be 25 minus 10 plus 1. So that would be there would be 16 occurrences of this critical operation here. In our example, the n was 4. Right, so we have 16 minus 8 plus 1. So that's, 9? Okay, so if you went and used your debugger and counted exactly how many times the flow of control got to this line, you'd see it's exactly 9 times. Okay, so some algorithms work better for different sizes of n. N might be big and might be small. Let's see what effect that has on an algorithm. Okay, so let's say we came up with this function to describe the algorithm. And let's say the function was equal to 1000 n. Again, these functions I'm talking about are just some little bit of arithmetic here that kind of states the problem in terms of the size n. Okay, so let's say we had this algorithm and we decided we could describe it by saying it's 1000 n. Whatever n is, we're going to do 1000, basically 1000 operations per each item. And then we had another algorithm. Let's say we are comparing this other algorithm that's g of n, and maybe we say that's n squared plus n. Okay, so now the question is, well, which one is better? Okay. Well, one thing we could do is we could start plugging some numbers in for n. Let's start when n is small. Right, so let's say n is equal to 10. So if we plug in 10 for n, well then, let's see, 1000 times 10, that's going to be 10,000. Okay, and if we plug in 10 for g, so let's see, 10 times 10 is 100, plus 10 is 110. Okay, so it looks like g is superior here because, again, we're counting the number of times that some critical operation has been executed, and it seems like the algorithm G is a lot more efficient, right? Because we're doing less processing. However, when problems are small, we usually don't care about the performance of the algorithm, right? So if what this means is we spend 0.000001 seconds to execute this one, and this one's a little bit better, and we only spend this amount of time. Well, these are really small amounts of time. So small that it probably doesn't matter. Okay, who cares if we save a nanosecond here or there? We usually only care when the problems are big. Okay, n was 10. That's a pretty small value. We have to re-examine these algorithms and say, well, what happens when n is really big? So let's put some bigger numbers in here. Let's say f of 100,000. Okay, so if we plug 100,000 into f, 1,000 times 100,000 is 100 million critical operations. Right? Right, that makes sense. 1,000 times 100,000 should be 100 million. Okay, but if we plug in 100,000 to G, we get 10,100,000. Okay, or I'm just going to round down to about 10 billion critical operations. So in this case, G really is 100 times slower. Okay, we're doing 100 times more work in the algorithm G than we are in F. Okay. Let's plug in some more numbers. Let's say let's get even bigger. Let's say we're going to do something with a size n of 1,000,000. Okay, so f of 1,000,000, this is about 1 billion critical operations. But if we plug 1,000,000 into G, n squared plus n, okay, that's about 1 trillion critical operations. So now G is 1,000 times slower. Before, G was only 100 times slower. Now G is 1,000 times slower. It gets worse and worse. The bigger n gets, the larger the difference between the algorithms described in F and G. So when n gets big, we might be talking about the difference between program finishing in 5 hours versus 5 days. Okay, there really is a dramatic difference. And if you were to actually look at a graph of F and G, F would look something like this, and G would look something like this. So it's true, there was this point here where G was actually superior. Right? When n was small, G actually outperformed F. But as n got really big, you'll see that if you plug in a value here, there's just a huge difference between n and G. I'm sorry, F and G. G is much, much worse than F in terms of the number of critical operations that are going to be executed. Okay, so the efficiency of an algorithm describes the relative efficiency as n gets large. Okay, we don't really care about when n is small, we only care about when n is large. And if we have an algorithm that we can describe like with some mathematical function, maybe 3n squared plus 4n plus 7. This might be the exact mathematical function that describes an algorithm. But usually we're really only interested in the highest order term. The highest order term, in this case 3n squared, dominates the overall value when n gets big. So we can basically ignore all but the highest order term. And then the coefficient, right, that actually doesn't affect the highest order term too much. So a lot of times we just ignore that too. And we say that this function, 3n squared plus 4n plus 7, is really just an n squared algorithm. Because when n gets large, it's the n squared part that is going to dominate the amount of work that happens. So we say an algorithm is on the order of n squared. And whenever we talk about this, we call this big O notation. The O being kind of on the order of. Okay, this doesn't tell us anything about the number of seconds that an algorithm takes to complete, but it does tell us how the algorithm performs as a function of n. Okay. And there's some common algorithm types or classifications. So we have, I'm going to list these from best to worst. A big O of 1 algorithm, we call that constant time algorithm. Okay. And what that means is n has no effect on the algorithm at all. We'll look at one or two algorithms that are like this in a minute. Next we have big O of a log n, and we call this logarithmic time. Okay, so this is not as good as a constant time algorithm, but we'll see it's better than the next one. The next one is called a linear time algorithm. Okay. Then the next very common algorithm type would be n log n. Okay, so remember, a logarithm is kind of like 2 to what power is equal to a number. Right, so 2 to what power is equal to 1,000? Well, it's about 10. Okay, so we'll see in a second that logarithmic functions, they grow over time, but they grow very slowly. Okay, the next we have an n squared, or a quadratic time. We might have a cubic, n to the third, would be cubic time. And by far the worst would be an exponential algorithm. Okay, so just to give you kind of a sense of what these algorithms would look like. Again, let's say n is on this scale, and on this scale we're talking about the amount of work that that is done, or the number of critical operations that we're counting. Okay, constant time would look like this. Okay. So again, it doesn't matter if n is small or large. It takes the same amount of work no matter what. Logarithmic time. A logarithm, like I said, it does grow over time, but it grows pretty slowly. Next would be linear time. So this might be something that looks like this. Again, it's growing over time, and it's growing faster than a logarithm. But we'll see shortly that it's growing slower than, say, the next one is n log n. That one would maybe look something like this. Then we have quadratic, might look like this. Cubic would rise even faster. And then exponential would grow tremendously faster than even the cubic. Okay, so many of the algorithms that we're going to talk about in data structures, we'll be able to measure. We'll say, oh, it's either a constant time algorithm, or a log n, or a n log n, or an n squared. And again, these are kind of listed in from best to worst. So if you can come up with an algorithm that performs in constant time, that's much better than the competing algorithm that does the same thing, but it does it in cubic time. Right? So remember, constant time, n doesn't even play a factor. Doesn't matter if n is big or small. So often there's a trade-off made for the efficiency of an algorithm versus how hard it is to come up with a solution. So let's look at a couple simple problems here. Let's say we're trying to find the sum of the numbers from 1 up to n. Okay. I may have even asked you to write this program in class at one point. The easiest way to do this would be to say, all right, we're going to have a variable called sum, and we'll start it at 0. And then we're going to want to basically march through the numbers 1 up to and including n and sum these things together. So we can have this counter called I. We'll say, well, I is less than or equal to n. Okay. So I is going to span from 1 up to n. And what we can do is take the value currently in sum and add to it the value I, and then store the whole thing back in sum. Okay, and by the time we get out of this loop, okay, whatever's inside sum here, that's going to be the sum of the numbers from 1 to n. Now this is a big O of n algorithm, because the amount of work really depends on the size of n. Okay. Also, this code is very simple and easy to understand. It's easy to debug. However, there's another way to solve this problem. Okay, let's look at the numbers maybe 1 through 8. And if we start pairing these off, so 1 and 8, say 2 and 7, 3 and 6, and 4 and 5. Notice if you summed all these pairs up, 8 plus 1 is 9, 7 plus 2 is 9, 3 plus 6 is 9, 5 plus 4 is 9. Okay. What you might notice is that no matter what the size, whatever the number is, all these pairs always sum up to n plus 1. Right? So the n plus 1 is always the sum of the pairs. Now next we say, well, how many pairs are there? And let's see, it looks like there are 1, 2, 3, 4 pairs. That turns out to be n over 2. Okay. So if we multiply these two things together, n plus 1 times n over 2, that's going to give us the sum of the numbers from 1 to n. Okay, so if we plug in our number 8 here, 8 plus 1 is 9, times 8 divided by 2 is 4, 9 times 4 is 36. So if you were to sum all these numbers, 1 and 2 is 3, plus 3 is 6, plus 4 is 10, 15, 21, 28, 36. The sum of the numbers from 1 to n can be described with this little bit of arithmetic here, n plus 1 times n divided by 2. Okay, so another way to write this code is just to say n plus 1 times n divided by 2. Now this is a big O of 1 algorithm. This is constant time. The amount of processing does not depend on the size of n. Whether we plug in 8 or 8,000, it's still just this one bit of arithmetic. Whereas if we used the number 8,000 over here, we'd have to do 8,000 iterations of this loop. This big O of 1 algorithm, though, does require you to be clever. So not everyone would have just noticed this relationship between the numbers. In fact, a very famous mathematician figured this out a long time ago. So this code is not as clear, I think, and readable and easily understandable to your average programmer as this code is over here. This, I think, anyone can kind of understand. So sometimes you might not be clever enough to really improve an algorithm. And other times you'll know that another algorithm exists that is much more complex, but you'll still choose the inefficient one because it's simpler. Okay, let me give you another example. Let's say we wanted to search through a list of sorted numbers. Okay. Well, one thing we could do is we can use linear search. This basically just says start at the beginning and look for a particular item. And if we find it, great. If not, we'll know that it's not there. So linear search looks something like this. This is searching through n items in an array. So our critical operation would look like this. This kind of characterizes the work that's being done inside the algorithm here. So is the item in the array equal to what we're looking for? If it is, maybe we will return true. And if we ever do happen to fall outside the loop, we can maybe return the value false. Okay, so in the best case, there'll be one critical operation. So if we just happen to get lucky and the very first item in the array is the one we're looking for, then we will only have executed this critical operation once. The worst case is when what we're looking for is not on the array, in which case we do n critical operations. Right? We get all the way through the end and realize, oh, what we're looking for is not there. And the average case is somewhere around n over 2 critical operations. So on average, you're going to get lucky. Sometimes it's going to be in the first half. Other times you'll be less lucky. The item we're looking for is either not on the list or it's in the second half. Okay, so what we would do is we would characterize this as a big O of n algorithm, right? Because if we factor out all the coefficients and the likelihood of it being in the first half or the second half, again, it's about n over 2, but we'll take out the 1/2, and this becomes a big O of n algorithm. Now, binary search works on a sorted array. So remember, this linear search was a linear search of a sorted array. If they're not sorted, we can't use binary search. But if we do have a sorted collection, we can use the binary search algorithm, which looks something like this. Okay, while the start is less than or equal to the end, we'll pick a middle value by summing start and end, dividing by 2. Okay, so middle will always be the value directly in the middle of start and end. And then we can check, this is our critical operation, if the value of the array at position middle is exactly equal to our search value. Okay, if that's true, we can say yes, the search value was found. Okay, but if that's not true, next we'd check if the value in the middle, okay, if that's greater than the search value, okay, so if the item in the middle is greater than what we're looking for, okay, then we don't know for sure that the item is in the list. Okay, but if it is in the list, it's going to be in, let's see here, if the array in the middle is greater than what we're looking for, then I think what we would do is move the end to be the middle minus 1. And if that's not true, well, then what we're looking for is going to be in the second half of the list, and we can move the start. So we'll just say middle plus 1. So that's our binary search algorithm. And just to give you a sense of how this performs, right, let's kind of imagine we had an array of, let's say, 1,000 items. I call this the phone book algorithm because every single time we go through the loop, we throw out half of the remaining items. So if we had 1,000 things that we were searching, because we either get lucky or we throw out half of the remaining items. We go from having to search 1,000 items to searching 500, then 250, then 125, then about 62, about 31, about 15, 7, 3, and 1. Okay, so the very best case is we'd execute this this critical operation, this comparison here, exactly one time. Our worst case is what we're looking for is not on the list, and we had to do this 1, 2, 3, 4, 5, 6, 7, 8, 9, about 10 times. Okay. So what is the log of 1,000? Well, it's 2 to what power is equal to 1,000? Well, it's about 10. Okay. So what that means is this binary search algorithm, if you have the sorted list, it will take you about 10 critical operations. You'll only execute this line about 10 times. And that's in the worst case. The average case will be somewhere between 1 and log n. So again, what we would say is, well, binary search, that's a big O of log n algorithm. Okay, again, because this, whenever you find yourself repeatedly having, cutting in half an item, that's what we call a logarithmic algorithm. So binary search is a big O of log n algorithm. Okay, so I always end this lecture with this question: is it better to sort an unsorted collection using bubble sort, which is an n-squared algorithm, and then use a binary search, which is a log n, or leave the collection unsorted and just use a linear search, which is a big O of n algorithm? Okay, so let me write this down here. Okay, so we said, now let's say we had an unsorted collection, and we could certainly sort it and then use binary search. Okay, so sorting would be n squared. Bubble sort is an n squared algorithm, and then the binary search would be log n, versus just doing a linear search of the unsorted collection. And we know that, of course, is an big O of n algorithm. Okay, so let's look at sorting and then doing a binary search. Well, I already said you always look at the highest term, so you could kind of ignore the log n here, and doing these two things together is a big O of n squared. So to sort the unsorted collection and do a binary search, that's really an n squared algorithm, whereas a linear search on an unsorted collection, that's just big O of n. That's remember, linear search, you just start at the beginning and you search until you either find it or you get to the end, and that's a big O of n algorithm. So clearly, what we should do if we have an unsorted list and we want to search through it is not sort it first, because sorting, that's the dominant part of the algorithm. It takes up the most amount of work, whereas a linear search is just a big O of n. So that would be the preferred thing to do.